Usually when we talk about a medical diagnosis, there's this expectation of just like absolute precision.
Right, it's a binary state.
Exactly. It
Oh,
feels almost like mechanical engineering, Like you break your arm, you go to the hospital, the x-ray shows that jagged white line on the screen, and the doctor just points at it, says, there it is.
yeah, it's broken or not broken, it's clean.
It's totally clean. It's undeniable.
And honestly, it's comforting. I mean, we fundamentally like things to be visible, to be categorized in these very neat, mutually exclusive little boxes. Our brains just, they crave that certainty.
But then, you step out of that clean mechanical world and you step into the inner workings of artificial intelligence, and suddenly the x-ray machine is broken.
Oh, completely broken.
Right. We're looking at a diagnostic landscape that is honestly just completely murky. We look at a machine making a decision, and we can't always just point to the jagged white line to explain, why it made that specific choice.
It is the absolute definition of diagnostic muddy waters. Because when you look under the hood of how a machine actually learns, you aren't looking at a clean binary system anymore. You're looking at, like, a living, breathing mathematical ecosystem.
Which is kind of terrifying.
Terrifying, yeah, or perhaps beautiful, depending on how you look at it. But the part you have to realize is that this ecosystem is incredibly sensitive to the environment we create for it. It is not just a calculator spitting out an indisputable 4 when you type 2 plus 2.
Right, right. Well, welcome to the deep dive. If you're tuning in, you are probably someone who is naturally curious. You're tired of hearing superficial tech buzzwords thrown around at dinner parties or in the boardroom, and you are ready for a true aha moment.
Absolutely.
Today, we are opening the black box of machine learning based on this incredibly dense, like 54-slide presentation we have on professional machine learning engineer fundamentals. We're going to find out exactly why that x-ray machine is broken, how machines actually learn, how they grade themselves, and, this is the crazy part, why the humans pulling the strings might actually be the biggest point of failure.
Yeah, the goal here is to really move past the vocabulary words. We want to understand the mechanics.
The brain mechanics.
Exactly. When a machine takes, I don't know, 1 million raw data points, learns to recognize a pattern and actually corrects its own mistakes, how is it doing that mathematically?
And I know the word mathematically might scare some people, but don't panic.
No, don't panic at all. We are going to translate all of those intimidating concepts, things like, derivatives, cross-entropy, regularization in mechanics, you can actually visualize.
So before we can get into the really complex math of a machine correcting its mistakes, we first have to, map out the territory.
Right, set the stage.
Because people toss around the terms AI and ML all the time, often in the exact same breath, as if they're perfectly interchangeable synonyms. But they aren't, right? If AI is the entire conceptual universe of a smart machine, where does machine learning actually sit in that?
Well, it helps to visualize this as a set of concentric circles, like a Russian nesting doll.
Okay, nesting dolls. I like that.
So the largest outermost doll, the biggest circle, is artificial intelligence.
Yeah.
That's the grand umbrella term. It encompasses literally any technique that enables a computer to mimic human intelligence or logic.
So, anything slightly smart.
Basically. Like a simple computer program from the 1980s that plays chess by searching through a massive hard-coded list of if-then rules. Technically, that is AI.
But it's not learning anything, right? It's just following a script that some guy typed out.
Precisely. Which brings us to the next nesting doll inside that big one, and that is machine learning, or ML. This is a very specific subset of AI. Instead of a human programmer writing out millions of explicit if-then rules, we give the machine a massive amount of data and a general architecture, and we let the machine figure out the rules for itself.
So the machine derives the logic from the data.
Exactly. And just to complete the map, there's an even smaller doll inside machine learning called deep learning.
Right, which is where we get into complex neural network inspired by the human brain, which we'll get to. But I want to park right there in the middle in machine learning.
Sure.
Because within that space, there seems to be this massive fundamental line drawn in the sand between how we teach these machines. We have supervised learning on one side and unsupervised learning on the other.
Yeah, that is the great divide. And the difference boils down entirely to one thing, really: labels.
Okay, let's unpack this. Let's start with supervised learning. The slides describe this as being task-driven. It has a specific goal, and as you said, it uses labeled data. So I'm assuming this means we're kind of holding the machine's hand through the whole process.
Very much so. In supervised learning, you are giving the machine the raw data, but you're also giving it the answer key.
Got it.
So you don't just feed it a million image pixels. You say, here is an arrangement of pixels, and by the way, the correct label for this is a cat. And then here's another arrangement, and the correct label is a dog.
Right.
The machine's entire job is to look at the data, look at the answer you provided, and figure out the mathematical relationship between the two.
It's trying to reverse engineer the logic, basically.
Exactly. So that later, when you hand it a picture of a cat without a label, it can apply the logic, reverse engineered, and guess the label correctly.
Now, within that supervised space, the material points out two distinct ways we ask for that answer: classification and regression.
Right.
Classification seems highly intuitive. We're predicting a categorical variable. Like you said, sorting a new picture into a discrete bucket. Cat bucket or dog bucket.
Right. It's categorical, true or false, spam or not spam, red, green, or blue.
But regression is predicting a continuous numeric variable, so we aren't putting things in buckets anymore.
No, you're predicting a specific number on a sliding scale. A classic example is forecasting future sales.
Okay.
You're giving the machine historical data past sales, seasonality, marketing spend, and asking it, how many units will we sell next Tuesday? You don't want a category. You want a highly specific number, like 4,251.
Okay, that makes sense. So predicting tomorrow's temperature, estimating the future price of a stock, calculating the exact amount of time a road trip will take, these are all regression problems.
You got it. The answers are known historically, and we are training the machine to find them. That is supervised.
Right. But contrast that with unsupervised learning, because this is described as entirely data-driven, and crucially, it uses completely unlabeled data to identify patterns.
Yeah, this is where things get slightly more philosophical, honestly. Well, in unsupervised learning, you are intentionally withholding the answer key. You hand the machine a massive, chaotic pile of raw data, and you essentially say, I have no idea what is in here. Tell me what you see. Find the hidden structures.
If I can try an analogy here, tell me if this works. Supervised learning feels like giving a student a highly structured textbook with an answer key in the back. They can constantly check their work.
Right.
But unsupervised learning feels like taking that same student, dropping them in the middle of an absolutely massive, unorganized library without a map, and just telling them, walk around and see if you notice anything interesting.
I like the library analogy, but with one major caveat.
Okay, what's that?
The student you dropped in the library has absolutely no preconceived notion of what a book even is.
Oh, wow.
Yeah, they don't know what words are. They don't know what paper is.
That's a profound distinction. They're basically an alien.
They are starting from pure mathematical scratch. But what they can do is measure things. They might notice that certain objects in the library have identical dimensions.
Right, okay.
They might group all the hardcover books together, completely unaware that they are books, just knowing that their physical properties are highly correlated. They're discovering inherent structure without human bias telling them what to look for.
And the real-world applications of this are fascinating. The slides dig into 3 subcategories of unsupervised learning, and they really show exactly how powerful this can be.
Definitely.
The first is clustering, which is exactly what it sounds like, right? Mathematically grouping data points together based on similarity.
Yeah, a classic business application here is customer segmentation. Imagine you have a database of 10 million customers. You have their age, their income, the time of day they usually shop, what items they click on, but you have no labels.
Right, because if you already knew who was a bargain hunter or a luxury buyer, that would be supervised learning.
Exactly. So you unleash a clustering algorithm, something like k-means, clustering on this raw data. The algorithm plots every single customer in a multidimensional mathematical space and just looks for dense groupings.
So it just finds the crowds.
Right. It might naturally find a tightly packed cluster of people who are aged 22 to 25, live in urban zip codes, and make 80% of their purchases after 11 p.m. on Fridays.
Wow.
And you, the human, didn't even know this demographic existed. The machine discovered the cluster organically.
That's incredibly powerful for marketing. I mean, you didn't ask it to find night owls. It just noticed they mathematically huddled together.
Exactly.
Okay, the next unsupervised subcategory is association. This is described as identifying underlying relationships. How is that different from clustering? Aren't we just grouping things again?
Not quite. Clustering groups the entities like the customers themselves. Association finds hidden rules connecting the items or the events. Have you ever heard of the classic beer and diapers scenario?
Vaguely. Isn't that like an old retail myth?
It's often used as an anecdotal illustration of association rule learning. The idea is that a grocery store feeds millions of transaction receipts into an unsupervised model. The algorithm isn't looking at who the customers are. It's strictly looking at what items appear on the same receipt. And it might discover a strong mathematical correlation. People who buy diapers on a Thursday night are statistically highly likely to also buy a six-pack of beer.
Oh, I see. So they move the beer aisle closer to the diaper aisle to maximize that impulse buy. It's finding the hidden connective tissue between seemingly unrelated variables.
Yes. It's discovering rules like if A and B occur, then C is highly likely to occur alongside them.
That is wild. The third subcategory of unsupervised learning is the one that sounds the most daunting to me. Dimensionality reduction.
Ah, yes.
The definition is literally just reducing the number of dimensions. And the classic example given in the slides is taking a massive set of variables for an insurance quote and compressing them down using something like principal component analysis, or PCA.
Right.
Can we unpack this? Because if an insurance company has 100 data points on me, my age, credit score, car color, zip code, isn't more data always better? Why would we want to reduce the dimensions?
That is a very intuitive question. But in machine learning, there is a very real phenomenon known as the curse of dimensionality.
The curse of dimensionality, that sounds super ominous.
It is, computationally speaking. If you have 100 different variables, you are plotting your data in a 100-dimensional mathematical space.
Yeah.
It is incredibly difficult for an algorithm to find meaningful patterns in that much sheer noise. Furthermore, many of those variables are likely redundant.
Redundant how? Like they mean the same thing.
Think about a house you're trying to value. You have the total square footage. You also have the number of bedrooms, the number of bathrooms, and the size of the living room.
Okay.
Those four distinct dimensions are all heavily correlated. They're essentially all whispering the exact same underlying concept. This is a big house.
Ah, I see. So feeding the machine all four of those metrics is just making it do extra math to learn the exact same thing.
Exactly. Dimensionality reduction algorithms, like PCA, are designed to mathematically squish this data down. They find the overlapping characteristics and fuse them together into a smaller set of brand new, highly informative variables.
So it combines them.
Right. It might take those four room size metrics and compress them into a single new dimension called, let's say, size index. So you can reduce 100 dimensions down to 10, making the computation lightning fast without losing the core narrative of the original data.
It's like taking a highly detailed 3D object and looking at its 2D shadow. I mean, you lose a dimension, but you still immediately recognize the shape.
That is a phenomenal way to visualize it. You're preserving the variance, the essence of the data, while stripping away the bloat.
Okay, so we've thoroughly mapped the territory. We know if we're handing the machine an answer key or dropping it in the library. Now I have to figure out how the machine actually processes this information. Let's look inside the brain of the machine. Let's talk about neural networks.
Yes. This is where we transition from the theory of what we want to do to the actual architecture of how a machine computes it.
And there is a serious alphabet soup of acronyms here in the presentation. ANN, DNN, CNN, RNN, LLM.
Lots of N.
Lots of N's. Let's not just list them. I really want to understand why we need so many different structural variations. Let's start with ANN, Artificial Neural Network.
The ANN is the foundational blueprint.
Yeah.
It is the standard vanilla neural network that everything else is built upon. It passes information strictly in one direction, from input to output.
And a DNN, Deep Neural Network, is just an ANN, but deeper, meaning more layers.
Yes. When people talk about deep learning, the deep literally just refers to the number of hidden layers between the input and the output. A simple ANN might have one or two hidden layers. A DNN might have dozens, hundreds, or even thousands. This allows it to learn incredibly complex hierarchical features.
But then we get into specialized architectures, like CNN, convolutional neural network. These are always associated with images, right? Facial recognition, medical x-rays, self-driving car camera.
Almost always, yes.
My question is, why do we need a special network for images? Why can't I just take the millions of pixels in a photograph, feed them into a standard deep neural network, and ask it what the picture is?
You technically could, but it would be horribly inefficient and likely fail. Think about how a standard DNN works. Every single input connects to every single neuron in the next layer.
Right.
If you have a high-resolution image, you have millions of pixels. If every pixel connects to 1 million neurons, the number of mathematical weights your computer has to calculate instantly skyrockets into the trillions. It's computationally catastrophic.
So it's just too big.
It's too big, and more importantly, a standard DNN loses spatial relationships. If you feed pixels in one by one in a massive line, the network doesn't know that a dark pixel was directly above a light pixel in a 2D grid. It loses the concept of a corner or an edge.
Oh, and an image is nothing but spatial relationships. An eye is an eye because of how the pixels sit next to each other, not just because they exist in a vacuum.
Exactly. A CNN solves this by using something called convolutional filters. Instead of looking at every pixel at once, it slides a small mathematical magnifying glass, say a 3x3 grid, across the image, analyzing tiny patches of pixels at a time.
So it scans it.
Right. It explicitly looks for spatial patterns. Is there a vertical edge here? Is there a curve here? It retains the 2D spatial awareness while vastly reducing the number of connections needed.
That makes so much sense. Okay, what about RNN? Recurrent neural network. These are for sequential data where order matters, like predicting the next word in a sentence or predicting stock prices over a week. Why does a standard network fail here?
Because a standard network has amnesia.
Amnesia.
Yes. In a standard ANN, each input is processed in total isolation. If you feed it the word the, it processes it. If you feed it the word cat, it processes it. It has no memory that the came right before cat.
But human language is entirely dependent on what was just said. If I say, I grew up in France and I speak fluent, you instantly know the next word is French because you remember the beginning of the sentence.
Exactly. An RNN introduces memory. It has loops built into its architecture. As it processes current information, it simultaneously takes the output from the previous step and feeds it back into itself. It maintains an internal state or memory of what it has seen so far in the sequence.
Which brings us to the final acronym, LLM, Large Language Models. This is the tech behind the advanced chatbots that have taken over the world recently. Are these just massive RNNs?
Surprisingly, no. While they deal with sequences, LLMs largely moved away from traditional RNNs because RNNs struggle to remember things from very far back in a long paragraph.
They lose the thread.
Right. Modern LLMs use a different architecture called a transformer. Transformers process the entire sequence at once, rather than word by word, and use a mechanism called attention to mathematically weigh how important every word is to every other word in the text, no matter how far apart they are.
Okay, alphabet soup decoded. But to truly understand how any of these work, we need to go back to the foundation, the vanilla ANN. Let's map out exactly what happens inside one of these layers.
Let's do it.
We have an input layer where the raw data comes in. Let's say we are predicting the price of a house. Input 1 is the square footage. Input 2 is the number of bedrooms.
Right. And these input nodes are connected to the next layer, the hidden layer, bylines. Every single line connecting these nodes represents a weight.
And a weight is just a number, right? It represents how important that specific connection is. So as the square footage data moves down the wire toward the hidden layer, it gets multiplied by its weight.
Yes. If square footage is a massive predictor of house price, the machine will eventually assign a very large number to that weight. If the number of bedrooms doesn't matter as much, that weight will be smaller.
Makes sense.
The hidden layer receives these multiplied signals. It takes the square footage times its weight, plus the number of bedrooms times its weight, and it just sums them all together.
It adds them up. It's literally just taking a weighted sum of the inputs.
But here is the most crucial, mind-bending part of the entire architecture. The network doesn't just pass that sum forward. It takes that sum number and forces through something called an activation function.
Okay, activation functions. The slides make a huge deal out of this. If you don't understand the activation function, you cannot understand why deep learning actually works.
It is the secret sauce.
Let me try to break down the mathematical problem of not having one. If a hidden layer just takes a sum and passes it to the next layer, which takes a sum and passes it to the next layer, mathematically, if you have 50 layers of just multiplying and adding, you can algebraically condense all 50 of those equations down into one single simple linear equation.
Exactly.
You basically just have y equals mx plus b. It's middle school algebra.
Right. No matter how deep your network is, no matter how many millions of parameters you have, if you're only using linear operations, just multiplication and addition, the entire network collapses into a single flat linear function.
But why is that a problem? If the math is doing its job, why is a linear function bad?
Because the real world is almost never a straight line. Think about a graph trying to classify a dog versus a cat based on ear length and snout length. If you plot all the dogs and cats on a graph, you are going to be able to draw one perfectly straight line that separates all the cats on the left and all the dogs on the right.
The data points are going to be mixed together in a complex, overlapping blob.
Right. The boundary between cat and dog in that mathematical space might look like a squiggly circle or a sharp zigzag. A linear function can only draw a straight line. It is fundamentally incapable of learning complex curved boundaries. If you don't break the linearity, your deep neural network is effectively useless for complex tasks.
Enter the activation function. It takes that linear sum and it deliberately warps it. It bends the math to create a curve. Let's look at the actual functions used to do this, starting with the most famous one used in hidden layers, ReLU, which stands for rectified linear unit. The math behind this is shockingly simple, isn't it?
It is remarkably simple, which is why it is so powerful. The rule for ReLU is just this. If the summed input number is less than 0, the output is forcefully changed to 0. If the input is greater than 0, the output is just the number itself.
Wait, really? So if the math spits out -50, ReLU just says, nope, you are 0 now.
Exactly. It acts as a switch. It simply turns off any neuron that has a negative value.
But how does that introduce a curve that just sounds like a flat line on the floor that suddenly shoots up at a 45-degree angle when it hits 0?
It introduces a corner, a sudden change in trajectory. And when you combine millions of these little corners across thousands of neurons, the network can approximate incredibly complex, smooth curves.
Oh, I see.
More importantly, because ReLU just turns negative neurons entirely off, it creates what we call sparsity. Not every neuron is firing at once. This makes the network exponentially faster and cheaper to compute without losing its ability to learn complex patterns.
That is brilliant. Okay, what about the sigmoid function? This one looks like a very elegant, smooth S-curve.
Sigmoid is heavily used when you need to output a probability. Its mathematical formula takes any number you give it, whether it's negative 10,000 or positive 10,000, and it gracefully squashes it into a value strictly between 0.0 and 1.0.
So it's perfect for binary classification, like a spam filter. 0 means it's definitely not spam. 1 means it is absolutely spam. If the final layer of the network uses a sigmoid function and it spits out 0.85, the machine is essentially saying, I am 85% confident this email from a Nigerian prince is spam.
Precisely. It translates abstract mathematical sums into a readable human percentage.
But here is where I always get stuck. Sigmoid is great if I only have two options, spam or not spam. But what if my neural network is trying to classify an image, and it needs to choose between three things? A cat, a dog, or a horse.
Okay.
If I just use three different sigmoid functions, one for each animal, it might say I'm 80% confident it's a cat, 70% confident it's a dog, and 90% confident it's a horse. That doesn't make any sense. It adds up to 240%.
You've just perfectly articulated the need for our next activation function, Softmax. You cannot use independent sigmoids for mutually exclusive categories. If it is definitely a horse, the probability of it being a cat must go down. They are linked.
So how does Softmax fix that?
Softmax looks at the raw, unsquashed scores the network generated for all three animals simultaneously. It applies a mathematical transformation that turns all three scores into probabilities between 0 and 1, but with one critical constraint. The sum of all the probabilities must equal exactly 1.0 or 100%.
So it forces them to share the probability pool. It forces the network to weigh the options against each other. It might output 70% horse, 20% dog, and 10% cat. It forces a cohesive decision.
Exactly. Softmax is the standard activation function for the final output layer of almost any multi-classification problem. And there's one more you should know. Tanh, or the hyperbolic tangent.
The graph for Tanh looks identical to the sigmoid S-curve, but instead of squashing numbers between 0 and 1, it squashes them between -1 and +1.
Yes. Tanh is highly useful in hidden layers when you want your data to be centered around 0. It allows a neuron to output a strongly negative signal, a strongly positive signal, or a neutral signal right around 0. In many architectures, this zero-centered nature helps the next layer learn much faster than a sigmoid would.
Okay, so we have built the brain.
Mm.
Data flows in, gets multiplied by weights, summed up, bent by ReLUs in the hidden layers, and finally squashed into a neat percentage by a softmax in the output layer. The machine proudly spits out a prediction. It looks at a picture of a chihuahua, runs millions of calculations, and confidently declares cat.
A classic misclassification.
Right. It's wrong.
Mm-hmm.
But here is the multi-million-dollar question that forms the entire basis of machine learning. How does the machine know it's wrong? How does it know it messed up? And more importantly, how does it fix it?
This is where we introduce the harsh reality check of machine learning, the loss function, also known as the cost function.
In a supervised learning model, we have the machine's prediction, and we have the actual true label from the answer key. The cost function sits between them like a judge.
It is a mathematical formula that calculates the precise distance between what the machine guessed and what the true reality actually is. We refer to this distance as the error or the loss. The single overriding goal of any machine learning model is to make that loss number as close to zero as absolutely possible.
And just like we have different types of problems, we have different formulas for judging them. Let's look at a regression problem first, predicting a number, like our house price. The standard cost function here is MSE, mean squared error.
Right. Let's break down how MSE works mechanically. Suppose the machine predicts the house will sell for $300,000. The actual sale price from the answer key is $350,000. The machine takes the predicted value, subtracts the actual value, and gets an error of negative $50,000.
But then the formula tells it to square that error. Why square it? Why not just use the absolute value? If I take the absolute value of negative 50,000, it's just a positive 50,000. Why do we need the math of squaring it?
Two very important reasons. First, yes, it guarantees the number is positive. If you guessed too high by 50,000 or too low by 50,000, squaring it results in the same massive positive penalty. You don't want positive and negative errors canceling each other out when you average them across the whole dataset.
Because if it's over by 50K on house A and under by 50K on house B, the average error is 0. The machine would think it's perfect when it's actually terrible.
Exactly. But absolute value fixes that too. The reason we square it instead of using absolute value is about punishment. Squaring an error heavily penalizes large mistakes compared to small ones. Let's use smaller numbers.
Yeah.
If your error is 2 and you square it, your penalty is 4. If your error is 10 and you square it, your penalty is 100.
Whoa. The error only increased by 5 times, but the penalty increased by 25 times.
Yes. Squaring creates an exponential penalty curve. It mathematically forces the machine to prioritize fixing its most catastrophic, wild guesses first, before it worries about fine-tuning the predictions that are already pretty close.
That makes perfect sense for predicting numbers. But what about classification? Going back to our Chihuahua example, the machine predicted a probability distribution using Softmax. It said it was 80% confident it was a cat, 20% confident it was a dog. The true answer is 100% dog. How do you measure the distance between cat and dog? You can't subtract a dog from a cat and square it.
No, you can't. Which is why classification problems use a totally different cost function called cross-entropy loss.
This is a brilliant piece of mathematics that comes from information theory. Cross-entropy doesn't measure the distance between numbers. It measures the distance between two probability distributions.
Okay, walk me through how that actually works.
In the answer key, the true distribution is perfectly certain. 0% cat, 100% dog. A probability of 0 and 1. The machine's distribution is 0.8 for cat, 0.2 for dog. Cross-entropy uses logarithms to compare these two states. It specifically looks at the probability the machine assigned to the correct answer. In this case, the machine only assigned a 0.2 or 20% probability to it being a dog.
So it knows it was way off.
But here is the genius of the logarithm in cross-entropy. If the machine assigns a very low probability to the correct answer, the logarithm drives the penalty through the roof. It approaches infinity. Cross-entropy severely punishes a model for being highly confident in the wrong answer.
So if the machine said, I'm 51% sure it's a cat, 49% sure it's a dog, it's still wrong, but the penalty is relatively small because it was basically guessing. But if it says, I am 99.9% sure this Chihuahua is a cat, the cross-entropy loss absolutely slams it with a massive penalty for being arrogantly incorrect.
Exactly. It forces the machine to not only be right, but to be appropriately confident in its rightness.
Okay, so the cost function, whether it's MSE or cross-entropy, has graded the test. It gives the machine a massive penalty score. The machine knows it's failing. What next? How does a massive penalty score actually translate into the network fixing itself?
This is where we arrive at arguably the most important algorithm in all of deep learning: backpropagation.
Backpropagation. Propagating the error backward. We know the error at the very end of the network. How does the machine get that information back to the beginning? Let me try an analogy. Imagine a CDO at the end of a long assembly line realizes the final product is defective. That's the cost function. Backpropagation is the CEO marching backward down the assembly line, yelling at the final manager, who then yells at the middle managers, who then yell at the individual floor workers, telling everyone exactly how much they messed up so they can change their behavior for the next product.
That analogy captures the spirit of the cascade. But we need to inject the mathematics to really understand the brilliance of it. The CEO isn't just randomly yelling. They are using calculus specifically, the chain rule, to distribute the blame with mathematical precision.
The chain rule, so it's calculating exact proportions of blame.
Yes, the output layer made the final wrong guess. Backpropagation calculates exactly how much each individual weight coming into that output layer contributed to the final error. It might find that the weight connecting to neuron A caused 80% of the error, while the weight from neuron B only caused 20%.
So it knows neuron A needs a massive adjustment, and neuron B only needs a tiny tweak.
But it doesn't stop there. Once it knows neuron A is to blame, it steps backward again into the hidden layers. It asks, okay, which weights feeding into neuron A caused it to pass such a bad signal? It uses the chain rule to multiply the derivatives backward, layer by layer, all the way to the input. By the time it reaches the front, it has calculated a highly specific adjustment value for every single weight in the entire network. Millions of individual tweaks, all perfectly calculated to lower the final error on the next try.
That is staggeringly complex, and yet it leads us to our next major hurdle. Backpropagation calculates the direction we need to move the weights to lower the error, but it doesn't necessarily tell us exactly how far to move them. We need a strategy for applying these tweaks.
We need an optimization algorithm, and the standard engine for this is called gradient descent.
The classic visualization for gradient descent is a 3D bowl. Imagine a yellow, sloping, curved surface, like a deep valley or a crater. The entire surface of this bowl represents the cost function. The higher up you are on the walls of the bowl, the higher your error. The worse your predictions are. The absolute bottom of the bowl, the lowest point in the valley, represents the lowest possible error. That is where your neural network is perfectly tuned. The goal is to get to the bottom.
Right. When you initialize a neural network with random weights, you are effectively dropping a ball onto a random spot high up on the wall of this bowl. The machine is blindfolded. You can't see the bottom, but it needs to get there.
And backpropagation provides the tool to feel the slope. It calculates the derivative, the mathematical gradient, at that exact coordinate. It's like the blindfolded machine tapping its foot on the ground, feeling the steepness and realizing, okay, downhill is to my left.
Yes, the gradient is a vector that points in the direction of the steepest descent. To lower the error, the machine simply takes a step in the exact opposite direction of the gradient. It takes a step downhill.
But here's the catch. The machine knows the direction. But does the machine decide how big of a step to take? If I know downhill is to my left, do I take a tiny 1-inch shuffle step, or do I take a massive 10-foot flying leap?
This is a profoundly important vulnerability in the system. The machine does not decide the step size. The algorithm calculates the gradient, but the length of the stride is determined by a variable called the learning rate.
And who sets the learning rate?
You do? The human engineer sets the learning rate before the machine even turns on. Is a fixed structural rule.
Wait, really? Before the machine even looks at a single piece of data, I have to guess how big its steps should be. What happens if I guess wrong?
If you choose poorly, the entire multi-million-dollar training process will fail. Let's look at the two extremes. If your learning rate is too small, if you force the machine to take microscopic shuffle steps, it will absolutely head in the right direction, but it will take an eternity to reach the bottom of the bowl. It might take months of computing power, costing hundreds of thousands of dollars in cloud computing fees to converge on the solution.
That's bad. But what if I just make the learning rate massive? What if I tell it to take giant leaps to get to the bottom faster?
That is even worse. If the step size is too large, the machine feels the slope, takes a massive leap downhill, but it completely overshoots the bottom of the narrow valley and lands high up on the opposite wall.
Oh, no.
Now it's on the other wall. It calculates the gradient again, realizes downhill is back the other way, takes another massive leap, and overshoots again. It bounces back and forth across the ravine, getting higher and higher on the walls. The error doesn't go down, it explodes toward infinity. The model diverges entirely and destroys itself.
So finding the Goldilocks learning rate is absolutely critical. And this entire cycle, taking a batch of data, doing a forward pass to guess the answer, calculating the cost, backpropagating the error, and using gradient descent to take one step down the bowl. Doing that across your entire data set one full time is called an epoch.
Yes, a single epoch is one full lap through the material. A model might train for 10 epochs, or it might train for 10,000 epochs, slowly inching the way to the bottom of the bowl.
This revelation that the step size is set by the human before training even begins brings us to a really crucial philosophical division of labor in machine learning. It's the difference between what the machine controls and what the human controls. In the industry, this is defined as parameters versus hyperparameters.
This is arguably the most important distinction for anyone trying to understand why AI isn't just a magical black box that builds itself. It requires architectural intent.
Let's break it down. Parameters are the internal variables. These are the millions or billions of weights and biases inside the neural network. The defining characteristic of a parameter is that the machine has full autonomy over it. The machine adjusts the parameters during training via backpropagation. It's what the model learns.
The machine is the master of its parameters. You do not manually set the weight of a specific neuron in layer 42. You let the gradient descent algorithm find it.
But then we look at hyperparameters. These are the structural rules. How many hidden layers does the network have? Are we using ReLU or Sigmoid activation functions? What is the learning rate? How many epochs are we going to run? The defining characteristic here is that the human decides these, and they are locked in before training starts. It's how the model learns.
Hyperparameters are the architectural blueprint of the maze and the rules of engagement for running it.
We talk about artificial intelligence in the media as if it's this independent, self-governing entity. We anthropomorphize it. But really, the human engineer is the puppet master. The machine only controls the micro-adjustments. The human builds the maze, decides what the walls are made of, and dictates how big the machine's strides can be. If a model completely fails to learn, if it bounces out of the bowl, is it really a machine error, or is it fundamentally a human error?
In almost every case, a model failing to converge is a failure of human hyperparameter tuning. The machine is just blindly executing the calculus based on the blueprint you gave it. There is no magic formula that tells an engineer, for this specific medical data set, you must use exactly 8 layers, a learning rate of 0.001, and train for 500 epochs. It's entirely data dependent.
So how do you know what to set them to?
Immense human intuition, experience, and relentless trial and error. You run experiments. You train a small version of the model with one set of hyperparameters, check the results, tweak the learning rate, change the activation function, and try again. The intelligence of the artificial intelligence is heavily bounded by the intuition of the human engineer designing it.
Okay, so the human runs the experiment, sets the perfect hyperparameters. The machine tirelessly adjusts its millions of parameters over thousands of epochs, and finally we arrive at the bottom of the bowl. The loss is minimized. We have a fully trained model. Now comes the moment of truth. How do we actually evaluate if it's a good model? In school, you get a single pass-fail grade, like an 85% on a math test. But machine learning evaluation has to be more nuanced than just saying the model is 85% accurate, right?
Absolutely. A single blanket accuracy percentage is one of the most dangerously misleading metrics in all of machine learning. Depending on the context of the problem, an 85% accuracy could mean the model is ready for deployment, or it could mean the model is completely worthless and actively dangerous.
Let's start with evaluating regression problems, where we are predicting continuous numbers. We talked about mean squared error earlier as a cost function for training, but for final evaluation, engineers often use RMSE, which is root mean square error.
Yes. RMSE is simply taking the square root of the final MSE value. By taking the square root, you translate the error metric back into the original units of your data, making it interpretable for humans.
Right. If I'm predicting house prices in dollars, squaring the error gave me squared dollars, which makes no physical sense. Taking the root brings it back to regular dollars. So if my RMSE is $10,000, it means my model's predictions are off by an average of $10,000.
But the key characteristic of RMSE, because it still relies on that squared math underneath, is that it remains highly sensitive to outliers.
Explain that. Why does RMSE care about outliers more than something like MAE, mean absolute error?
Think about it mechanically. Let's say you have a model predicting the temperature for 10 days. For 9 days, it is off by exactly 1 degree. On the 10th day, it is off by 10 degrees. If you use mean absolute error, you just add up the errors, 9 plus 10 is 19, and average them. The MAE is 1.9 degrees. It smoothly absorbs that one bad day.
But if we use RMSE, we square the errors first.
Exactly. The 9 small errors squared are just 1 squared, which is 1. But that single 10-degree error squared becomes 100. Suddenly, the sum of errors explodes to 1 over 9. When you average that and take the root, the RMSE will be significantly higher than the MAE. The single massive outlier drags the entire score down violently.
So why is that useful? Wouldn't we want a metric that doesn't get ruined by one bad day?
Not if that one bad day is catastrophic. If you are predicting the temperature to prevent a citrus crop from freezing, being off by 1 degree all week is perfectly fine. But missing a massive 10-degree plunge means your entire crop dies. If you care deeply about avoiding large catastrophic errors, you used RMSE, because it will scream at you if the model makes even a few massive mistakes.
Context dictates the math. I love that. Okay, so that's predicting numbers. But evaluating classification problems, putting things in buckets, requires a completely different tool. We can't use RMSE to evaluate a dog versus cat classifier. We use something called the confusion matrix.
The confusion matrix is brilliant because it forces you to look exactly at how your model is failing, not just that it is failing. It breaks the errors down into specific types.
Let's visualize a simple 2x2 grid. We are evaluating our medical model that detects a rare disease. The columns represent what the machine predicted. The rows represent the actual reality. So we have 4 possible intersecting quadrants, 4 possible outcomes.
Let's walk through the easy ones first, the correct predictions.
Top left quadrant. The model predicts the patient has the disease, which is positive, and the reality is they actually do have the disease.
Yeah.
That is a true positive. Good job, machine. Bottom right quadrant. The model predicts they are healthy, so negative, and they are actually healthy. That is a true negative. Also good job.
The diagonal is where you want all your numbers to be. But the other diagonal, the errors, is where things get complicated.
Bottom left quadrant. The model rings the alarm and predicts the patient has the disease. But reality shows they are perfectly healthy. The model cried wolf. This is a false positive, also known in statistics as a type 1 error.
And finally, the top right quadrant. The model gives the all clear, predicting the patient is healthy. But reality shows they actually have the deadly disease. The model missed it completely. This is a false negative or a type 2 error.
Having these 4 distinct numbers allows us to move beyond a single accuracy percentage and calculate 2 highly specific metrics that are constantly at war with each other: recall and precision. Let's break down the mechanics of these two, because this is where the rubber meets the road in deploying AI.
Let's start with recall. The formula for recall is true positives divided by the sum of true positives plus false negatives. In plain English, recall looks at reality first. It asks, of all the actual true positive cases that exist in the real world, what percentage did our model successfully find?
It's a measure of thoroughness. Did we find everything we were looking for?
Exactly. Now look at precision. The formula is true positives divided by the sum of true positives plus false positives. Precision looks at the model's claims first. It asks, when the model raises its hand and confidently shouts, I found a positive case, how often is it actually telling the truth?
It's a measure of trustworthiness. If the alarm goes off, should I panic? To really cement the difference between thoroughness and trustworthiness, there is a vivid analogy used in the industry involving fishing nets. Let's say you are tasked with fishing in a murky lake. You know for a fact there are exactly 100 prized fish in this lake. These 100 fish are our actual positive cases.
Okay, 100 real fish. Let's look at scenario 1. Fishing with a massive wide net. You drag this giant net across the entire lake, you pull it up, and you count your catch. You caught 80 fish. But because the net was so huge and dragged along the bottom, you also scooped up 80 heavy rocks.
Let's calculate the metrics. For recall, which is thoroughness, out of the 100 real fish in the lake, you caught 80 of them. 80 divided by 100 is 80%. Your recall is excellent. You found almost everything.
Look at your precision, your trustworthiness. You have 160 total items in your boat. 80 fish plus 80 rocks. Only 80 of those items are actually what you claim they were. 80 divided by 160 is 50%. Your precision is terrible. Half the time your net said, I caught something good, it was lying to you.
High recall, low precision. You caught the fish, but you have to sort through a mountain of garbage to find them. Now, scenario 2. Fishing with a tiny, perfectly targeted spear gun or a tiny specialized net. You dive in, you take your time, and you only strike when you are absolutely certain. You come back to the surface, you have exactly 20 fish and 0 rocks.
The math flips entirely. Recall. Out of the 100 real fish in the lake, you only found 20. Your recall is a miserable 20%. You missed 80% of your targets. You are not thorough at all.
But precision. Out of the 20 items you claimed were fish, all 20 are actually fish. 20 divided by 20 is 100%. Perfect precision. When you claimed you had a fish, you were right every single time. Low recall, high precision.
This represents a fundamental, inescapable mathematical trade-off in machine learning. You almost never get both. If you want to increase recall, cast a wider net, you will inevitably catch more rocks, lowering your precision. If you want to increase precision, be more strict about what you call a fish, you will inevitably miss some real fish, lowering your recall.
So as the human puppet master setting up this model, you have to choose which metric matters more. And that choice is entirely dependent on the real-world consequences of your errors. Let's go back to our medical model, detecting a deadly, fast-moving, rare disease. Do I want the wide fishing net or the small fishing net?
For a deadly disease, you absolutely must prioritize high recall.
You want the wide net. You need to find every single possible case of the disease.
Even if it means catching rocks. Even if it means my precision is terrible.
Yes. Think about the physical reality of a rock in this scenario. A rock is a false positive. The machine flags a perfectly healthy person and says they have the disease.
Yeah.
What happens in the real world? The doctor calls the patient in, they are anxious, the doctor orders a secondary, more expensive blood test, the test comes back negative, and the doctor apologizes for the scare. It's an inconvenience, it causes some anxiety, and costs a bit of money.
But what is the alternative? If we use the small net, we prioritize precision. We hate false positives.
If you prioritize precision, you tighten the net. The machine only flags people it is 99% sure are sick. Your false positives drop to 0. But your recall plummets. You are now generating false negatives. The machine looks at a sick person's scan, isn't quite confident enough, and says they are healthy.
Oh. And the doctor sends a terminally ill patient home with an all clear, and they miss their window for life-saving treatment.
Exactly. For a deadly disease, a false negative is fatal. A false positive is an annoyance. Therefore, you deliberately tune the model to have high recall, sacrificing precision to ensure you don't miss the fish.
That is incredibly sobering. But let's flip it entirely. Let's look at a scenario where we want the exact opposite. Let's look at the AI that filters spam in your Gmail inbox.
The stakes here are different, which changes the math completely. What happens if Gmail uses the wide net high recall for spam?
If they use high recall, they want to catch every single spam email in the universe. But we know a wide net catches rocks. In this case, a rock assazative. A false positive is a legitimate, important email from my boss or my doctor or my wife getting flagged as spam and dumped into the junk folder.
And how angry are you when you miss a critical deadline because your boss's email went to spam?
Furious. A false positive in my email is unacceptable. I don't want to dig through the garbage to find my real life.
Exactly. Gmail users demand high precision. You want absolute trustworthiness. You want to know that if Google puts something in the spam folder, it is definitively 100% spam. To achieve that perfect precision, Google must use the small net. They have to make the spam filter very strict.
And by making it strict, they sacrifice recall, meaning they will generate false negatives.
Right. A false negative here means a real spam email slips past the filter and lands in your main inbox. Google intentionally designs the system to allow a few spam emails to slip through to your inbox, just to guarantee they never accidentally filter out a legitimate email. Context dictates the math.
This tug-of-war is constant. And it brings up one final evaluation metric before we move on, AUC, or area under curve. We've talked about balancing precision and recall, which often means picking a specific threshold like only flag an email as spam if the model is 90% confident. But AUC seems to evaluate the model independent of that threshold.
That's precisely why it is used. Finding the perfect threshold, 50% confidence, 80%, 99%, is a business decision made after the model is trained. But as an engineer, you want to know if the underlying model is fundamentally good at separating the classes, regardless of where you draw the line.
The technical definition often used is, if we pick a random positive sample and a random negative sample, what's the probability the model scores them in the correct relative order?
Right. An AUC of 1.0 means the model perfectly separates all the cats from all the dogs. An AUC of 0.5 means the model is literally just flipping a coin and has no ability to distinguish between the two. It gives you a single aggregate score of the model's pure discriminatory power. Okay, so listening to all of this, understanding how harshly these models are judged by cost functions and confusion matrices, it's incredibly tempting to try and cheat the system. If I'm a human engineer, my career depends on this model. I want an AUC of 1.0. I want a model that catches 100% of the fish and 0% of the rocks. I want a model that gets 0 errors on the training data. But there's a massive trap waiting for anyone who chases that perfect 0 error score.
It is the greatest nemesis of the machine learning engineer.
Oh.
Overfitting. Beware of overfitting as you increase your model's complexity.
Let's visualize this. Imagine a graph with a bunch of red dots scattered in a rough U-shaped pattern, like a smile. We want our neural network to draw a line that predicts the pattern of these dots. We have 3 options. Option 1, the underfit model. The neural network just draws a perfectly straight, flat, horizontal blue line right through the middle of the dots, completely ignoring the curve of the smile.
That is a model that is too simple. It lacks the mathematical complexity. Perhaps it didn't have enough hidden layers or it didn't use activation functions properly to learn the underlying pattern. It failed to learn.
Option 2, the fit model. This is the gold standard. The neural network draws a beautiful, smooth blue curve that gently swoops down and back up, perfectly capturing the general U-shaped trend of the dots. It doesn't physically touch every single red dot, but it clearly understands the mathematical rule governing them.
It has abstracted the general principle. It learned the signal.
But then we have option 3, the overfit model. Instead of a smooth curve, the neural network draws this chaotic, jagged, wildly squiggly line that violently zigzags up and down, doing loop-de-loops just to ensure it perfectly intersects with every single individual red dot on the graph. On paper, its error rate on those dots is 0.0%. It is perfect.
And it is completely, utterly useless in the real world.
It sounds so counterintuitive. If it hits every single dot perfectly, hasn't it learned the data better than the smooth curve?
No, because it hasn't learned the data. It has memorized the noise. Let's go back to our student analogy. Imagine a student preparing for a final exam by taking a practice test. The fit student takes the practice test, gets a few wrong, but learns the underlying formulas and concepts. When the final exam comes with brand new numbers, they do great because they understand the logic.
The overfit student doesn't bother learning the concepts. They just memorize the exact answers to the exact questions on that one specific practice test. If question 1 is about trains, the answer is C. They score 100% on the practice test.
Exactly. But when they sit down for the final exam and the teacher changes the train speed slightly, the memorized answer C is completely wrong. The student fails spectacularly because they learned the specific examples, not the general rule. The squiggly line is the machine memorizing the exact coordinates of the training data, including all the random noise and outliers.
So how do we catch a model cheating like this? If it's scoring 100% on its training data, how do we know it's overfit before we deploy it into a hospital?
This is why the golden rule of machine learning evaluation is: you can never, ever trust a model's performance on the data it trained on. You must evaluate the final model with independent, unseen test data.
You have to hold back a chunk of your data in a vault. You take your massive data set and slice it up. You have an experimental box, which contains your training data, the practice test, and your validation data, which you use to tweak your hyperparameters. But then you have a separate locked box called the test data.
The machine is never allowed to see the test data during the training epochs. The backpropagation algorithm is never allowed to use it to update weights. It stays locked away until the very, very end.
And then you spring the final exam on it.
Exactly. If your model scores 99% accuracy on the training data, you might think you are a genius. But when you run the locked test data through it, if the accuracy plummets to 60%, you have concrete proof that the model overfit. It memorized the practice test and failed to generalize to reality.
But what if I don't have a massive data set? What if locking away 20% of my rare disease scans means the machine doesn't have enough data to learn in the first place?
That is a very common problem. And the solution is a technique called cross-validation. It is a clever way to maximize small data sets without cheating. Instead of a single locked vault, you divide your data into, say, 5 equal chunks or folds.
Okay, folds A, B, C, D, and E.
You train the model on folds A, B, C, and D. You lock away fold E as the test. You get your score. Then you wipe the model's memory completely. You start over. But this time you train on A, D, C, and E, and you use fold D as the lock test.
You rotate the vault.
Exactly. You repeat this 5 times, rotating the test fold until every single piece of data has been used as an unseen test exactly once. Then you average the 5 test scores together. It gives you a highly robust, trustworthy evaluation of how the model will perform in the real world without wasting any precious data.
Okay, so cross-validation helps us detect overfitting. But how do we actually prevent it from happening mathematically? How do we physically stop the neural network from drawing that chaotic squiggly line? This brings us to the final, incredibly elegant concept we need to cover: regularization.
Regularization is the mathematical cure for overfitting.
Yeah.
And it requires a fundamental shift in how we calculate the cost function.
Up until now, we said the cost function just measures how wrong the prediction was. It calculates the error. But regularization changes the equation entirely. The formula becomes: minimize the error of the data, P log S, a penalty for the complexity of the model.
This is profound. We are explicitly telling the machine, accuracy is no longer your only goal. Simplicity is now equally important.
To stick with our student analogy, regularization is basically the teacher taking points off the final grade if the student's essay is overly complicated and rambling, forcing them to find a simpler, more elegant answer. You got the right answer, but you used 50 convoluted steps when you could have used 3. I am penalizing you for the unnecessary complexity.
That is a perfect translation.
A model that draws a massive, jagged, squiggly line requires huge, extreme mathematical weights to yank the curve up and down so violently. A model that draws a smooth, gentle curve uses much smaller, more stable weights. Regularization mathematically punishes large weights.
The two most common types of regularization used in deep learning are L1 and L2. Let's dig into how they actually achieve this mathematically. What is L1 doing differently than L2?
Let's start with L1 regularization, also known as lasso. L1 calculates its penalty by taking the absolute value of all the weights in the network and adding them to the cost function.
Okay, so if the weights get big, the penalty gets big, and the machine tries to shrink them during gradient descent to lower its score.
Right. But because L1 uses absolute values, the gradient, the downward pressure, is constant. It pushes the weights down, 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 and it doesn't slow down as they get near zero. In fact, L1 will frequently push a weight all the way to exactly zero.
Wait, if a weight becomes exactly zero, doesn't that connection effectively cease to exist?
Exactly. L1 regularization acts like a ruthless bouncer. If a feature isn't absolutely critical to the final prediction, L1 drives its weight to zero, completely severing the connection. It performs automatic feature selection. If you feed it 100 dimensions of housing data and 20 of them are useless noise, L1 will just turn those 20 features off. It leaves you with a sparse, highly interpretable model.
That's amazing. It prunes the dead branches off the tree. So what about L2 regularization, also known as ridge?
L2 calculates its penalty differently. Instead of absolute values, L2 takes the squared value of all the weights and adds them to the cost.
We're squaring things again. We know what squaring does from our MSE discussion. Squaring heavily punishes large numbers.
Exactly. If a weight gets massive, say a weight of 10, the L2 penalty is 100, it screams at the backpropagation algorithm to shrink that specific weight immediately. But as the weight gets smaller, the penalty shrinks exponentially. If the weight is 0.1, the penalty is a tiny 0.01.
So unlike L1, which pushes weights all the way to absolute zero, L2 just pushes them to be very, very small. It doesn't sever the connection. It just turns the volume down on almost everything, preventing any single weight from dominating the network.
Precisely. L2 keeps all the features active, but shrinks their impact, resulting in a very smooth, stable, generalized model. It actively prevents the massive mathematical spikes required to draw the overfit squiggly line. It is a constant mechanical tug-of-war between fitting the training data and keeping the internal math as simple as possible.
It forces the machine to find elegant, generalizable rules rather than chaotic, hyperspecific ones. It keeps the machine's ego in check.
It does.
This has been a massive, incredible journey through the actual mechanics of this technology. We started by defining the territory, distinguishing machine learning from the broader umbrella of AI, and understanding the profound difference between the supervised answer key and dropping a model into the unsupervised library to find hidden dimensions.
We then built the brain itself. We moved past the alphabet soup of CNNs and RNNs and looked at the core anatomy of an artificial neural network, specifically how activation functions like ReLU and Softmax bend the linear math, forcing the network to learn the complex curves of reality.
We watched the machine learn through the harsh reality check of cost functions, using cross-entropy to punish arrogant mistakes. We trace those errors backward through the chain rule calculus of backpropagation, and we watch the machine blindly navigate down the 3D valley using gradient descent.
We confronted the reality of the puppet master, realizing that human hyperparameters like the learning rate and the architecture itself dictate the structural rules of the game long before the machine adjusts a single internal parameter.
We learned how to measure success, realizing that depending on whether we are casting a net for a rare disease or filtering our Gmail, we have to endure the agonizing trade-off between recall and precision. And finally, we explored how to stop the machine from memorizing the practice test, using cross-validation to lock away the final exam, and L1 and L2 regularization to mathematically force the network into simplicity.
It's an incredibly elegant, if imperfect, ecosystem. And looking over all of this, synthesizing everything we've unpacked about the math, the architecture, and the human element, I'll leave you with a final thought to mull over.
Please do.
We spent this entire deep dive exploring how mathematically incredible it is that machines can learn. They can calculate millions of derivatives, navigate multidimensional landscapes, and bend linear space. But remember the gradient descent bowl. Remember that the step size, the learning rate, the very speed and trajectory of that machine's learning is a hyperparameter. It is chosen by a human before the machine even turns on.
As AI models get infinitely larger and more complex, moving from simple networks to massive language models with hundreds of billions of parameters, this raises a profound question. Is the true bottleneck to artificial superintelligence the computational power of the machines? Or is the actual bottleneck the limited intuition, the flawed trial and error capacity of the human puppet master setting the hyperparameters? The machine can only run the maze as well as the human designs it.
Wow. If the height parameter is flawed, the supercomputer just fails faster. We started this deep dive talking about the murky, muddy waters of diagnostic uncertainty, comparing a clean X-ray to the complex inner workings of a neural network. I think we've successfully charted a path through those waters today. We've seen that the machine isn't magic. It is a direct reflection of the constraints, the mathematics, and the architecture we provide it. Thank you so much for joining us on this deep dive into the true fundamentals of machine learning. Keep questioning the architecture of the algorithms around you, keep looking for the human hands on the hyperparameters, and we will catch you next time.